Okay guys, in this video we are specifically going to try to factor a polynomial completely that with traditional factoring methods would fail to factor. So on this number 22 here we have g of x is this cubic polynomial, this four-nomial that traditionally we would look for a GCF here to see if there were one. There isn't a GCF. I also notice this has four terms, and if you attempt to try grouping with this one here, grouping works a lot of the time, but it doesn't work here. And so what we're going to do in this particular instance is use division to our advantage, and specifically our factor theorems, which we're going to mention here in just a moment. But it says show that the binomial is a factor of this polynomial, then factor the polynomial completely, which is our task here. We want to factor this completely. But what they have done here, or what I've done is I've given you a binomial to begin with here that is a factor of this thing. So one thing I want you to keep in mind is we're going to prove here in a moment that when we take g of x and we divide it by this x minus 2, what we get is some quotient, okay? But what we get is some quotient plus no remainder. And the way we look at this is, you know what, specifically I've got to put this over, not the divisor polynomial, but x minus 2. We say when I divide g of x by x minus 2, because it's a factor, then I would expect that I get some quotient plus no remainder over x minus 2, which in other words we would say is g of x divided by x minus 2 would just be some quotient and there would be no remainder. And so really what we're seeing is that if I were to rewrite g of x on its own, that is to take both sides of this equation times x minus 2, what we get is this general statement that says that, well, if x minus 2 is a factor, then g of x would be x minus 2 times whatever you got for an answer when you divided x minus 2 out of this. And so what you'll see here is that this really counts as the factored form of the original, and at this point we would have some quotient here that's smaller in degree than the original polynomial that we started with. Maybe we could factor it on our own, but the thing here is, as long as we know one factor, we could divide it out to find the other factor and use that information to write the original polynomial in factored form and try to factor it more completely. So we said that we would mention our factor theorem here. We say that this basically states that x minus k is a factor of f of x, a polynomial f of x, if f of k equals 0, which is kind of a crazy thing to say given that this is the factor theorem. But in essence, what this is stating is that, well, if x minus k is a factor, in this case, like x minus 2 was a factor, but generally speaking, if I said, you know, x minus k is some factor of this thing, then I'm going to get a quotient with no remainder, and then generally speaking, we say g of x is really equal to x minus k times the quotient that I got left over once I divided that out. Now, why is this important? Well, because when we're solving these things, we say that, well, let's set y equal to 0 and solve this. And in a factoring sense, whenever we're factoring things, what we're doing is we're taking each of these factors and setting them equal to 0, which in this particular instance, let's see if I can scroll down here, we would say that either x minus k equals 0, or the quotient of x equals 0, and it could have some zeros there, but the bottom line here is if you add k to the right side of this, we say that x equals k is one of our solutions here. So it basically means that this could only be a solution ever if this had been the factor in the first place. So we're going to use this to our advantage to help us factor here. I want you to see this. If we were to take this polynomial and say prove that x minus 2 is a factor, let's go ahead and set up our synthetic division array. In this case we can use synthetic division. And we're going to put a x equals 2 on the outside. So we would say that we have 2 times 1 is 2, plus 2 is 4, 2 times 4 is 8, plus negative 5 is a 3, 2 times 3 is 6, plus 6, negative 6 is a 0. And so what we said before was basically that x minus 2 could only be a factor if f of 2, or f of that x value, is a 0. And so that's what we proved here. We say x minus 2 is a factor because, you know, when you plug in an x value of 2, we get a height of 0. Now what we're left with is this x squared plus 4x plus 3. So what I want to make sure that we all write over here is basically this. Because x minus 2 is a factor, then the original polynomial can be written as x minus 2 times what we got when we divided x minus 2 out of this thing, which is this right here. And at this point, if I said, well, my goal is to factor this completely, this is some quadratic thing that I notice doesn't have a GCF. It's in quadratic form. And so we could factor this just like we would any three-termed thing and say, well, could I think of two numbers that multiply out to be 3 that have to be 4? And I think of two, I would say x plus 3 and x plus 1. So on this line right here where it says g of x in completely factored form, we're going to say, well, x minus 2 times x plus 3 times x plus 1. This would be a really, truly beneficial form to have this in, just because it would also helpfully or help us find the solutions of the zeros of this function. So really easy, just divide out the known factor and then factor the remaining quotient. Cheers.